Hi, let's discuss phasor diagram of a transformer. We already studied about ideal and practical transformer. So a ideal transformer is a transformer where all magnetic flux created by the primary winding links with the secondary winding. So there is no leakage flux and the coefficient of coupling will be unity. The primary and secondary windings will have zero resistances and the leakage of the windings is zero. The power transfer efficiency will be 100% and the permeability of the core will be infinite. And the transformation ratio or the turns ratio is equal to the ratio of its primary to secondary voltages. So this is the figure of an ideal transformer on no load. An ideal transformer is one which has no iron losses, no winding resistance and no leakage flux. That is, the secondary will be open circuited and under such condition, the primary is a coil of pure inductance. So when a sinusoidal voltage is applied across the primary, a current Im, which is magnetizing current, flows through it and lags behind the voltage V1 by 90 degrees. The current Im sets up an alternating flux phi in the core and it is known as magnetizing current. Here there are no losses, so the flux phi will be in phase with the magnetizing current. The flux phi will set up Im links with both the windings and induces EMF in them. The EMF induced in the primary opposes the voltage V1 and the back EMF limits this primary current. The EMF V2 induced in the secondary is 180 degrees out of phase with V1. So, the final conclusion is, in an ideal transformer, the primary draws a magnetizing current which lags the voltage by 90. The alternating flux phi is set up in the core which is in phase with Im. A self-induced EMF E1 is produced in the primary which opposes the voltage V1. A mutually induced EMF E2 is produced in the secondary which is in anti-phase with V1. Now, let's discuss next topic, practical transformer on no load. When the transformer is on no load and when the transformer is connected to the supply with the secondary open circuit, we can see a current called I0 which is the sum of Im and Iw. That means here in this case there exists a secondary MMF also. Due to that, secondary current sets up its own flux phi2. This flux opposes the main flux phi which is produced in the core due to magnetizing component of no load current. The flux phi2 reduces the main flux phi1 due to which the primary induced EMF E1 also reduces. The current I2 dash is in antiphase with I2. The current I2 dash sets up its own flux which opposes the flux phi2 and it helps the main flux phi. Therefore, when the transformer is loaded, the primary current I1 will have two components, IW and IC. The no load current I0 which lags V1, it has two components IW and IC. The magnitude of the induced EMF in the primary is E1 and E1 is drawn 180 degrees to phasor V1 and the no load current I0 is resolved into IW and Im. IW is equal to I0 into cos phi 0 and the second component Im will be equal to I0 into sin phi 0. Now coming to the practical transformer on load. When the transformer is loaded, the current I2 will flow through the secondary winding also. The magnitude and phase of I2 is determined by the load. If load is inductive, current will lag V2. If load is capacitive, current leads the voltage and for a resistive load, current is in phase with the voltage. So here I have represented three phasor diagrams for inductive load, resistive load and capacitive load. So I have discussed for inductive I2 lags E2, for resistive I2 is in phase with E2, for capacitive I2 leads E2 by phi 2, and also I2 dash is always in antiphase with I2. Actually the phi 2 is the angle between I2 and V2. So this is about phasor diagram of a transformer under no load and loaded conditions. So lecture notes on transformers and the complete unit is available in our website. So I have uploaded the complete 5 units of basic electrical engineering subject in my website. So it is very helpful to the students regarding your exam point of view. Thank you.